Thank you all for coming. My name's Craig Kaplan, for those of you who I don't know yet. I put this talk together because I didn't know much about the topic. And I have taken over stewardship of the forum, the ASRAS forum. And part of my vision for that talk is that it be sort of like a seminar where if they want, people can choose to give talks, and by that way learn how to learn the topic. So I'm not coming at this as an expert. I'm coming at it as somebody who's like one step ahead of you guys. And this is my way of learning. Putting things together and teaching them is the way I've always learned. So this is sort of my classroom, in a sense, my personal classroom. What I would like to do with the talk is talk over terms that you may hear bandied about all the time, but may not be totally sure what they mean, and take a little bit of a deeper dive into some terms that we'll come to. But the main sequence, HR diagram, nebulas, planetary nebulas, protostars, all of those we're going to look at to some greater degree. And we're going to look at the process of star formation, the classification of stars, and the HR diagram, which we'll talk about in greater detail. Life cycles of high and low average mass stars, and end of life events for high and low average mass stars. And finally, we'll touch upon the origins of the heavier elements that we see here on Earth and elsewhere in the skies. As I said in my introduction, this is a beginner. I'd like a stream of activities to run through ASRAS talks and activities that are labeled as beginners. So I just joined the Rochester Birding Association. If you go to their website and say, should I attend this talk or should I go on this hike and see these birds? Some of their talks they have labeled as for beginners, for people who are just getting started in the discipline. And they're meant to attract those people to that. And I'd like to create that kind of a track through ASRAS for folks. So this, in a sense, this talk is labeled as a beginner, and it's by a beginner. I asked some people to kind of help me put this talk together, and I think there are tons of folks in ASRAS who would be willing to mentor people who want to give talks like this by way of learning about it. And then since I gave the first talk for the forum, I had a family reunion here this week, and my daughter is a librarian at the Henrietta Public Library, and lo and behold, in the library is this book, which I now have. The library's loaned it to me, but I don't want to read it until I can read it to my grandson. So I'm going to hold on to it until he's ready, and then I'm going to read it. But we're not really babies, so I'll concede that we're going to change it to Astrophysics for Beginners in this particular talk. This is sort of the bedrock of the talk. It's the outline, and I'll keep referring to this diagram, but this really takes stars. Does this have a laser pointer on it, Mark?
Yeah, so the middle.
Middle is okay. So
it's not advancing pages, though.
Right. So it takes from the molecular crowd of protostars to the endpoints of all these stars, and we're going to take this piece by piece throughout the talk. So let's talk about the birth of stars first. So stars and planets, etc., are formed from interstellar gas and dust from the very beginning of the universe. And if you look at the various forms of interstellar gas, these are just the gas. These are star-forming regions. So a lot of these regions, especially here, you see new stars in formation because this gas is collapsing from gravitation, and as it collapses, the center towards which it collapses heats up, eventually reaching the point in which nuclear fusion can begin. This is a protostar here, where it's hot and emitting light, but fusion hasn't yet begun. So it's called a protostar, a star in formation, and then these are obviously the end results of this whole process, including our sun. Nebulas, which have already been talked about a number of times today. Various are defined as simply enormous clouds of dust and gas occupying the space between stars and acting as a nursery for new stars. The nebula comes from a root word that means mist, vapor, fog, smoke, exhalation. Wikipedia defines a nebula as a distinct luminescent part of the interstellar medium, which can consist of ionized, neutral, or molecular hydrogen, and also cosmic dust. Drive one of these left-handed, one of these right-handed. Nebulas are composed mainly of hydrogen, and they spectroscopically they identify different regions. So there are H2 regions that are mainly ionized hydrogen. There are H1 regions that are mainly neutral hydrogen, and molecular clouds mainly molecular hydrogen. So there are different types of hydrogen, but these all end up coalescing into stars. Nebulas are often the result of the end process of a star's life. So we'll go into that in greater detail, but as it's sort of like a phoenix phenomenon. Stars, as they die, give birth to additional stars. And it's a currently cyclical process. So as I said, the protostar is accumulation of gas and dust to the core. They heat up, causing the star to emit some light, but not nuclear fusion. Eventually, the combination of heat and pressure from gravity causes nuclear fusion to begin hydrogen into helium initially, and a star is born. If the star isn't the correct size to have enough mass to cause nuclear fission to begin, it becomes a brown dwarf, a failed star in essence. And the size needed is, if you were at Jeopardy last night, this was one of the answers, is that the size a star needs, the mass a star needs in order to initiate nuclear fusion eventually is about 0.08 times the size of the sun. This answer was expressed as 8% last night, but it was the answer. And at first, brown dwarfs were only speculative, but now they've actually identified them using telescopes that weren't available to people who first proposed that these could happen. And this is, I believe this is an actual picture of a brown dwarf here. What they look like.
It's an artist.
It's an artist? Okay, thank you. Pardon?
They're too small.
Too small to be seen from Earth.
Oh, right, okay. Yeah, I thought I'd read that Webb had looked at a couple of them, but thank you. And this reminds me that, again, as a beginner, there are a lot of folks in this room who know more about this than I do. So if I make a mistake, please correct me. That's the job of you guys. So I once worked with, I'm a physician. During my training, I worked with a cardiologist. And at the beginning of the month-long rotation, he said, I figure about 10% of what I tell you is going to be wrong, and it's your job to figure out which 10% it is. I probably still think things to this day that I misclassified as right from that.
So, Greg, so what happens? What eventually happens to a rock? If they're forming, but they're too small to actually initiate fusion?
I think they wander around. They could be captured into a solar system. Some people say that Jupiter is an example of one of these. I'm not sure it exactly is, but
the hydrogen in the core forms metallic hydrogen. And you have hydrogens on both sides of the periodic table, as it is in the periodic table. Hydrogen is also metal. And you get compact enough, and you get this metallic hydrogen core. And it's tremendously magnetic. And it creates its own little miniature solar system. I think you need 80 masses of Jupiter
to approach the brown dwarf.
to get to the point of
Yeah, that's what I've heard. It's just too small. All right, so once the star is born, once nuclear fusion begins, the size, luminance, temperature, and color of the star are all determined by its mass. And a critical feature that we'll run through all of this talk is that there has to be a balance between the inward pressure from gravity on the star and the outward pressure from heat and photons and other radiation that are emanating from the star, and that the star maintains its integrity through a balance of these. And I've on the next page should be a little better view of this. So this is outward heat and outward radiation and the balance of pressure. When the fusion decreases and that outward pressure stops, the star isn't shown. And we'll get to that in a little bit. But throughout most of the star's life, this balance holds until end stage begins. So back to this. So now we've talked about molecular clouds into protostars, and then we're going to move now to and brown dwarfs. And we're going to move now into first what happens in the life of a low mass star, and then what happens in the life of high mass stars. We're going to define the main sequence. I spent a long time misunderstanding this. I should say that my quote-unquote career in astronomy began when I was an intern. And I figured out that in order to survive internship, I was going to have to figure out something to do that wasn't medicine. And what I chose was astronomy. And each week, I would go out and memorize a new constellation. And I would constellation hop throughout the year. And by the end of the year, I knew a lot of new constellations. I then completely forsook astronomy until 2017 when I joined ASRAS, because I said, I'm going to retire. I'm not going to do medicine anymore. What am I going to do? Astronomy popped at the top of the list. So I joined ASRAS. Mark's been a friend through scouting for a long time. He got me into it, and here I am today. So, and for most of those 40, 50 years, I misunderstood what the main sequence actually meant. So we're gonna get into that today. That's one of the deep dives we're going to do. If you look at types of stars, initially before telescopes, all we had was the naked eye. And so this is an example that colorized, but people observe there are larger stars and smaller stars. People observe that there are stars of different color. And then they began to organize that perception. So the early classification schemes had initially assigned stars Roman numerals. Then they assigned stars in letter classifications A through Q. Some of the famous names are in here in the late 1800s, early 1900s, and they were based on the spectral characteristics of stars. And then again, they included stars A through Q. Any Jump Canyon significantly improved this whole thing in the early 1900s by throwing out all the letters except for these. And she organized this table. This became the Harvard classification, which is, except for one step, is our current method of understanding it. There are a couple letters that have been added after, but we're going to ignore those. And so you can see that this Vega relative chromaticity Vega is assigned a character of white, and any stars that are different from Vega are assigned relative. So these are all colors of stars relative to Vega being white. And there are several different things. This solar masses, M. Anytime you see a subscript 0 during this time, it refers to that characteristic of the sun. So M0 is the mass of the sun. So these O-type stars are more than 16 solar masses, 6.6 solar radii. Their temperatures are greater than 30,000, or the luminance is greater than 30,000, and they make up a very small proportion. You'll see that these larger, hotter stars on this end are relatively small, and that's for two reasons. One is not every star forms in a region with enough gas and dust to create a star that big. The other thing we'll see later in the talk is that these stars do not live very long. So there are stars that have been alive for almost the entire length of the universe, but the very, very large hot stars don't live very long. So the sampling of those is not good when we look at relative percentages. So because it's hard for them to form and they don't last very long, they account for a very small number of stars. One mnemonic has always been, or this OBAFGKC is, oh, be a fine gal or guy, kiss me. I found on the web one professor invited his class to submit, because he didn't like, as I don't like, the gender-based class, this particular mnemonic. He invited his class as a final project to submit alternatives to this particular way of running them. So I've written some of them down here. So only boring astronomers find gratitude knowing mnemonics. Oh boy, an F grade kills me. This is the one that I remember. Only brilliant astronomers fix grave Kaplan mistakes. There's a whole list of them. Those are just some of the ones that I kind of like. So the Morgan-Keenan system is the current system. It takes the Harvard classification and adds a numerical digit for temperature in each letter class. The temperatures numerically can be 0 to 9, coolest to hottest, and then adds, in addition, a Roman numeral digit for luminosity. And so our sun is classified as a G-type star in that system, a 2 in that system, and a V, a Roman numeral 5 in this. So that's the current system of classification. For the rest of this we're just going to stick with the Harvard Annie-Junkanian system, because the rest, one confuses me. It's a little too complicated. But to be fair, this is the actual current. If you get asked in next year's Jeopardy, what is the most current classification? The correct answer is, what is the Morgan-Keenan system? So just for future reference, just saying. The Hirschsprung-Russell diagram adds further clarity to this classification of stars. And I've tried to put the really important terms in red up here, so that we allude back to what I wanted to accomplish with this talk. So this was accomplished in the early 1900s. It looks at the relationship between absolute magnitude, or luminosity, and temperature. And it turns out that the spectral classes, the Harvard classification system, can all be mapped into this. So this is one example. There are a gazillion of these out here. I should also take I took most of these figures from Google Images. And so to be fair, I did not put anything in here that I could really tell was copyrighted. Because to be fair to everybody, down at the bottom here is the site that I got these from, to give them full credit for it, so I don't get accused of plagiarism. But this is the HR diagram. You can see up here, here's absolute magnitude. And I'm going to do a bit of a deep dive into magnitude. This is one of those things that I've had difficulty understanding. So we're going to take the next couple slides, we're going to look at magnitude, because it'll help clarify, I hope, for you. These stars, the majority of stars, ranging from brightest, most luminous, and hottest. So this is brightness, and you'll see that you may be used to x-y axis, the origin being less than as you extend up the axis. And here, instead of that, temperature increases as you approach the origin. So the hottest stars are here, whereas if you're used to constructing XY graphs, you usually would see hot, at least hot to hot. So if you organize it this way, the hot, very luminous stars are up here, and you can see there aren't a lot of them. The most common stars are in this section here, and most stars lie on this, which was called the main sequence. And so for a long time, as I heard people refer to this main sequence, I figured a star lived its life by proceeding along the sequence. That it started up somewhere here and ended up going down here to the end of its life. And it's not a sequence. A star, once it's formed, lives on that part of the main sequence until it begins end stage, at which point it leaves the main sequence. It doesn't follow the sequence. So as you think of the main sequence, it's just a place that begins stars, and the sequence refers to maybe all these classifications. And these classifications can be mapped onto here. So hot, large stars, O-class stars, through cool, low luminosity stars are out here on the very end. And so our sun, as you can see here, this luminosity scale is defined as the sun being a class of 1. So our sun lives right here, which is, again, I said a G-class star. So our sun is a G-class star living here in, people describe our sun as an average star. It is, it's right here in the main sequence in here. But our sun will not move up or down this sequence. Eventually, it will move out here and around in here, just to foreshadow the coming talk a little bit. Any questions about the main sequence? All right, so magnitude is a measure of luminosity or brightness. Remember, one of the scales of the Hirschsprung diagram is luminosity or brightness. And it turns out that the larger the numerical magnitude, the dimmer the star. So a star of 1 is much brighter than a star of 16, which is not the way I'm used to seeing scales operate. So, and negative stars are even brighter than very, very low number positively emitted stars. Oops, I keep doing this, sorry. Their magnitude can be apparent or absolute. So apparent magnitude is how bright a star looks to be from Earth. And distance makes a difference here. So very, very bright stars that are a long way away may have a fairly low apparent magnitude, whereas very, very relatively dimmer stars that are closer to Earth have a higher apparent magnitude. Absolute magnitude is how bright a star would be if viewed from a standard distance. So you correct all these magnitudes for distance by saying, okay, how would all these stars look if they were usually about 10 parsecs or about 32.7 light years away from Earth? So if you see a chart of absolute magnitude, you're not looking at what those stars will appear like from Earth. You're looking at it as corrected and on a standard scale. So you can compare stars one to the other without worrying about the distance. So again, I'm sure I'm doing a little bit of a deeper dive into things that confused me for a long time as I was trying to get into this, and that people who are much more advanced than I would kind of gloss over these, making the assumption that I understood it, and I was too wimpy to raise my hand and say I don't understand the magnitude thing. So this is my way of getting to understand that information. So the other thing to know about magnitude is that it's a logarithmic scale. So if you look at each step in magnitude increases or it changes luminosity by a log factor of 2.5. So magnitude 1 star is about 2.5 times as bright as a magnitude 2 star. Magnitude 1 star is about 2.5 to the second times, or 6.25 times as bright as a magnitude 3 star. So each step in magnitude is dramatically different, dramatically higher as one goes. So if you look at this on a scale, so this is the sun, which is apparent magnitude. Again, apparent magnitude on this scale looks like a negative 25, a very, very bright object, obviously. This is what the Hubble Space Telescope looks like. This is the unaided eye limit. So we can see objects. So if you look at star charts and they show a star that you're trying to look at, they will either label the star or have a relative size that you can look at scale at, excuse me, to figure out what magnitude the star is. And if it's if it's greater than a numerical magnitude of 6, you're not going to see with the naked eye no matter how good this guy's. And in Rochester, I would say that our unaided eye limit is probably considerably less because of light pollution and smoke and everything else. So just if you look at a star chart and see something that's got an apparent magnitude of greater than 6, no matter where you are, you're not going to see that without a telescope or some sort of visual aid. So that's sort of our deep dive into magnitude. And again, it's there because I didn't understand it. So back to the Hirschsprung-Russell diagram. And this is another way of looking at this. So a little more graphic representation of the size of these stars, or at least, so this is the main sequence here. These are O through M class stars. Here are the O and B stars, some of which can be very big. And again, progressively cooler stars of progressively less luminosity. as you go out here. And these stars have all left the main sequence. So we're happy for them, but they're in the end throes of life. And we're going to see what happens to these in the next few slides. These down here are white dwarfs. We're also going to explore what happens to them. Again, for those of you who were here for Jeopardy last night, this is one of the answers to what happens to a star in its end stage. And we'll see the answer to the other two. All right, so now in this stellar life cycle view, we've addressed the main sequence, and we understand what these stars are. We've talked about brown dwarfs. Now we're going to talk about this line here. What happens to low mass stars? Low mass is defined as less than 8 times the mass of the sun. So the sun is a very low mass star because it could be 8 times bigger and still be classified as a low mass star. This is a narrative description of end of life events, and then I'm going to show you this on the actual Hertzsprung-Russell diagram. But what end life begins when the star runs out of hydrogen in the core. So if there's no more hydrogen as the core fuel, and for millions and billions of years, the stars run on the amount of hydrogen in the core. But as it begins to burn, so that there are layers of hydrogen outside the core. So the core may have run out of hydrogen. It's mainly helium at that point. But the layers outside the star start burning, and when outer layers begin to burn, the star increases in size. And this is really a core concept. When stars increase in size, because they're burning outer layers, they increase in luminosity because they're bigger, but they get cool. So you can imagine if you look at, so luminosity and temperature are the Hertzsprung-Russell diagram, right? So as stars get bigger and more luminous, they go up that left-hand scale. But as they get cooler, they go back back towards the origin on the x-axis. So you can see what happens as these changes occur. So helium accumulates in the core. The core shrinks and heats, but doesn't undergo fusion at this point. Fusion layers outside the core swell, which increases luminosity, and the star leaves the main sequence at that point and enters what's called the red giant phase. The star continues along this red giant phase until something called the helium flash occurs, till the pressure and temperature in the core increases to the point that helium will ignite. And that's about 100 million degrees Kelvin. And that begins to fuse helium into carbon. And when that happens, it's a fairly dramatic event for that star, and the star changes characteristics and goes to a different place on the HR diagram again, which I'll show you. The core begins to collapse again. The star shrinks and enters the horizontal branch of the HR diagram. And after 7 million years, the star runs out of helium in its core. So the second source of fuel, helium, begins exhausted. As helium in the inner layer begins to fuse, and you continue having hydrogen fusion in the outer layer, again the star increases in size, a red giant, increases in luminosity, decreases in temperature of those outer layers, and enters the asymptotic giant branch. In its final phases, if the star is too small for further fusion, if it can't ever reach the point at which it can begin to fuse helium into other particles, it becomes a white dwarf, which is composed mainly of carbon, which is what you get when you fuse helium. And the next element is carbon. Larger stars are able to fuse carbon, oxygen, and even into neon. So they become white dwarfs, fusing the white dwarfs containing these elements. As the white dwarf shrinks and cools, however, it can't hold on to the outer layers, and these explode out away from the star, and that becomes a planetary nebula. Planetary nebula, another one of those terms that I misunderstood for many, many years, isn't a planet. It was named that by, probably I'm going to move this picture of me. It's blocking my notes. It was, let's see, William Herschel, thought when he looked at these through his telescope, he thought they were planets. And so he called them planetary nebula because they weren't quite as discrete as the planets were, but they were fuzzy, but he thought they were planets. So he called them planetary nebula, but they're not really planetary nebula. They have white dwarfs at their core rather than a planet. Yeah.
So a white dwarf turns into more white dwarfs?
No.
You said planetary nebula are white dwarfs.
Planetary nebula are the emitted layers of white dwarfs, and they expand out away, leaving the white dwarf at the center. But the white dwarf, as that gas of the outer layers is moving away, the radiation and photons from that white dwarf illuminate the gas, and that becomes the luminous nebula. Yes.
Would a good example of that be the ring nebula?
Yeah, and I'll show some examples of that. Yeah, yeah. There are a number of really gorgeous pictures, some of which are taken by members of our own club, that show these nebulas with the little white dwarf at the center. I think I have a couple of those coming up. So, yes. I saw that last night, actually. That's cool. I want to point out at this point that I've used two terms interchangeably: nuclear fusion and burning. And astronomers tend to use these terms. So for the purposes of this talk and most of what you'll read in astronomy, burning refers to nuclear fusion. And that's some astronomers. One of the things, I read a textbook on astronomy getting ready for this talk, and one of the things the author kept writing is that astronomers get stuck with some terminology that doesn't work, but they continue to use it. They just won't abandon it. So they'll refer to burning and nuclear fusion in the same. And some of these diagrams that I show you use burning and some use fusion. But again, for the purposes of this talk, they're the same. So if you look at this, so here is we'll take it to the sun eventually. So the sun runs out of hydrogen, begins to expand. Hydrogen begins to burn, continues to burn, but this time it's coming from a shell rather than the core of the star. And the star expands to become a red giant. And here, as it moves up, it's becoming more luminous, larger, but moving to the right, cool. So this star is turning redder, but more luminous because of its size, not because it's burning more brightly. And because we're looking at visual magnitude. This becomes the first red giant stage. That continues until because of the weight of the star and the heat of the hydrogen burning, the core reaches enough temperature as it continues to shrink and increase in temperature, it begins to be hot enough to burn helium, which we saw was 100 million degrees Kelvin. And this is when the helium flash. The star then moves here, and this refers to the horizontal phase. This is where helium's burning, and this is where it runs out of helium in the core. Helium in the shell now starts burning, and the star follows this. And if it's hot enough and has enough outer layers, it may emit a planetary nebula. But regardless, one way or the other, it will eventually progress to a white dwarf. And that's why all these white dwarfs are down here. They're relatively cool, they're very dense, and they're very small, so they're not very luminous. So they're at the bottom of the luminosity chart. They remain somewhere here in terms of their spectral classification. A lot of these have just carbon because they can't use anything further than that. Some of these have carbon through neon because the special characteristics will tell you what kind of white star cells were. So kind of to summarize, so here's the red giant star. There's no fusion in the helium core. The hydrogen, and just inert helium here. Here is the hydrogen burning, and here is the cool extended envelope around that hydrogen burning, and that's the red giant star. The horizontal branch star, the envelope remains hot. The hydrogen begins burning. It continues to burn in this shell, but now at the core, you've got helium burning. whereas up here it was just inert. So that becomes a horizontal branch star. Again, it moves to the left, hotter, remains about the same size, it stays there. The branch is horizontal for luminosity, but moving towards the hotter end of the spectrum on the curve. And then the final stage is on the asymptotic giant branch star, where you've got helium burning in the core after the helium flash. And carbon and oxygen here in the core continuing to burn, and it goes back up because it gets hotter and more luminous as these other elements ignite. But then it eventually exhausts those elements, not big enough or hot enough to fuse further elements, and pursues the path down to a white dwarf, whether or not it emits gases as a planetary nebula. Questions about that? Yeah.
Will you talk about the time scales of each of these steps?
Yes. Yeah, there will be.
Actually, one comment.
Yes.
Many books or you mentioned that you cannot go the outer skin, right? So it's growing. So it's opposite actually. Because the core is hotter, it has more pressure toward outside than gravity. Gravity is constant. Right?
Yes. So if I understand you, so you're right. You think about the balance of pressures. So the core is hot, but not as massive as it needs to be to get gravity to hold these outer layers in. So the heat is pushing the outer layers out, and gravity is insufficient to keep them in. So it loses the outer layers.
What I mean is gravity was almost same all the time.
Uh-huh.
But the pressure is increasing for outer skin going out.
Yeah, and that becomes the planetary nebula. Yes. Thank you. Oh, yes, I'm sorry.
Does the size of a planetary nebula indicate how far along in the process it is, or is that based on the actual size of the star? So if you compare like the ring nebula
Yeah.
to like the Helix nebula, they look very similar, but one is much larger than the
Right.
other. Is that because it's like emitted more gas over more time, or is it?
Yeah, I was going to add the time factor until you just did. Yeah, I think it's the characteristics of the star at the beginning of this. How long that gas has had to escape, because the gas is moving away very rapidly. Yes.
By the way, it tends to move out within a range of 6,000 to 10,000 years. So ring nebula could be 6,000 to 8,000 years old.
Mm-hmm. Great, thank you. So here's an example of some nebula. So this is the ring nebula here, and this is the white dwarf right at the center of it. This is the Cat's Eye Nebula, again, white dwarf right at the center of it. And the way these look different is an interaction between the gases emitted by the star and what dust is already out there, what other objects may be out there, what other sources of photons may be out there. And this is a really cool nebula called the Spirograph Nebula, again, with its white dwarf at the center. So these are all planetary nebula that have had pictures taken that are nice enough to see the white dwarf at the center. All right, so novas in type 1 supernova. So supernova occur if the white dwarf begins to acquire mass. And usually when it acquires mass, it's part of a binary system. So the white dwarf has enough gravity. These have a lot of gravity. They're very, very dense, very, very massive, even though small. And they can begin to steal hydrogen from their companions. So they begin to acquire a hydrogen envelope that they didn't have. So they can again steal fuel from the companion star, hydrogen flame. If fusion starts in the growing hydrogen shell, if the star continues to heat up and the hydrogen that is stolen from its companion star begins to burn, then it becomes a nova. And this can become a recurrent cyclical process as exemplified by T Corona Borealis, which everybody expects to go nova in the next couple months, really. They're predicting as late as sometime in September, but it even could have been a little earlier this summer. But it will, and it goes off every 80 years. So it has a companion star that it's stealing gas from, and it takes about 80 years until that point is reached where where helium fusion begins in its outer layers, and they go off as a nova. And then it gets a little small white star again. This whole process begins again. If, however, the white star manages to keep it together until it acquires enough mass to be 1.4 times the mass of the sun, which is called the Chandrasekhar limit, it heats up for carbon fusion to begin. And once carbon fusion begins, it starts quickly becomes unstable, collapses and explodes, and that becomes a type 1a supernova. So this Chandrasekhar limit will come up a couple times in the talk. I thought that it was going to be star power for 50 points last night. This is going to be the answer. I was all ready for that. So, but it wasn't. So, anyway, so the life of a white star can go one of two paths. It can either emit a nova, or it can, because what happens is as it emits a nova, it prevents itself from ever reaching this Chandrasekhar limit. So this can become a recurrently cyclical process. If it ever does reach the Chandrasekhar limit, then it explodes, and that's the end of the star. I mean, there is no white dwarf remnant when that happens. It's a very, very violent event. So again, this is the process. This is the white dwarf. This is the companion star, and this is the white dwarf stealing hydrogen and helium from the star. And again, if it ignites before the mass reaches the Chandrasekhar limit, it becomes a nova. If it acquires mass until it reaches that limit and surpasses it, and carbon in the core ignites, then it becomes a 1a supernova. So we're here. So we've just talked about the red giant phase becoming a binary red dwarf, in which case it can either emit a recurrent nova, or not all these are recurrent, but it can become that, or it surpasses that limit and becomes a type 1a supernova. This white dwarf out here is when the black dwarf out here is when the white dwarf has existed long enough that the heat remaining, even though it's no longer doing nuclear fusion, the heat is emitted fully, and it just becomes an empty core remnant that's not doing it. It's completely inactive, and there are a lot of these hanging around the universe. All right, so old age and death for high mass stars, which are greater than 8 times the mass of the sun. Again, these massive stars have short lifetimes. So our sun, by comparison, not massive, will live about 10 billion years. So stars that are 3 times the mass of the sun are expected to live around 600 million years. 5 times 100 million years, 10 times 20 to 30, 15 times 10, 25 times the mass of the sun. Their expected lifespan is only about 3 million years. So these guys are very bright and luminous for a very short period of time. Was that the answer? What you were looking for, Tony, was the expected duration of these events. I've also got the duration that happens when a supernova occurs, how quickly the various stages that occur.
I was looking for the actual, I mean, that tells you some,
Yeah.
not the individual steps as you move off of things. Those time scales, those are pretty short.
Yeah, they are very short. I've got those classified by what element is being fused in the star. So yes, you'll see that coming up. Yes.
What color would those massive stars be?
Well, the hotter they are, so they're going to be blue is the hottest they get. So probably blue, yellowish, but on the blue side for sure, because they're very big and very hot. Again, this is the divider between massive and not massive. So high mass stars, they begin end of life with higher core temperatures than the lower mass stars. So they don't undergo this helium flash phase. As stars exhaust hydrogen, the core shrinks. Again, core temperature rises, but the star expands, so luminosity increases. Core helium ignites again at around 100 million degrees Kelvin, and this process repeats itself because the star is massive enough to continue this process. Once the star is mostly carbon at the core, it's hot enough and massive enough to begin to fuse carbon into hydrogen, and eventually hydrogen into silicon and other elements. The other elements are the problem. We'll get to that in a second. But it can continue doing this, and it continues to move off the main sequence as it does so. Helium to hydrogen to helium takes about 10 million Kelvin. Helium to carbon takes about 100 million Kelvin. Carbon to oxygen, 600 million. Oxygen to neon, around 100 million. And neon to magnesium, greater than 100 million Kelvin. So stars that are able to achieve these kinds of temperatures can fuse progressively heavier elements until you get to iron. We'll see what happens when you get to iron in a second. So with the rise in core temperature, again, this process of the outer layers increasing in size and luminosity, but decreasing in temperature, the star moves up into the right of the main curve to form red giants. And the highest mass stars become supermassive red giants. So this is a little bit of a different diagram. We're going to be looking at these upper stars here. So again, 10 times the mass of the sun. Mass of star, hydrogen to helium. Helium begins burning, and the star moves to the right. Again, carbon begins burning here, and each time this happens, the star, the temperature of the core increases. The star increases in size, but decreases in temperature. So you see the decrease in the temperature moving to the right, and the increase in size moving to the upper. So it moves up until you get to a supernova. We're going to talk about how that happens, but it can get to the supergiant phase first. So these stars, one, don't undergo the helium flash phase that the smaller stars do, and they can continue burning elements beyond carbon. So they get bigger and hotter and can become as much as supergiants. Here, these are more than 100 times the radius of the sun up here, the ones that are out here. So this is another way of looking at this, and just to remind you of this, the need to balance the inward pressure from gravity and the outward pressure from photons and other forms of radiation. And these are the various levels, the various layers beside the core that are in these massive stars. The terminal stage begins when iron begins to accumulate in the core, because the reason the star shines, the reason photons are emitted, are because each time you fuse these elements that are not as heavy as iron, energy is released in the form of photons and other radiation. The problem is when you start making iron, it requires energy. So the fusion of iron requires energy. I'm sorry, the fusion of iron into heavier elements requires energy. So fusing elements into higher iron is the last stage in which you get photons and energy out of the process. Once you begin to try to fuse iron into heavier elements, it requires energy. So with this energy requiring type of fusion, the heat of the core decreases, and you stop producing photons and other radiation, and guess what? Gravity takes over. So the core temperature begins to decrease, as I said, outward pressure begins to, and what happens is once the star tries to begin fusing iron, the core collapse occurs extremely rapidly over the course of seconds, according to what I've read. And these are sometimes referred to as core collapse supernovas. because they occur because the core suddenly collapses. They're very violent, and they will collapse, and then there's a huge explosion. So these are called type 2 supernovas. They're extremely energetic. While they last, they may outshine the entire galaxy. The photo on the left was taken in 1987 during the supernova explosion, whereas this photo was taken before. So you can see how bright this supernova was compared to what existed in its place beforehand. Not identical pictures, but relatively close in time. So that's a type 2 supernova, is a core collapse. The process is rapid. So 10 to the 7th years, turning hydrogen into helium. 10 to the 6th years, turning helium into carbon and oxygen. About 1,000 years to get the oxygen, sodium, and magnesium. 3 years to get the magnesium. About a third of a year to get these elements, and about 5 days to get the iron. Once you hit the iron stage, the supernova occurs. So this is an accelerating, rapid process into death. It's not a lingering death. These supernovas. So enough energy is created in these supernovas to fuse heavier elements. So elements up until iron can be fused by stars. So whatever iron and less heavy elements exist in the universe can just be accomplished by stellar fusion. But all of these heavier elements have to come from some other process. And you can't get to those pressures and those heats without supernova explosion. So the vast majority of the heavier elements come from nucleosynthesis that occurs from supernovas. So this is a table, a periodic table that shows where most of these elements came from. So the green ones are from the Big Bang. The yellow, the blue ones are from lower mass stars, and all of these other colors are from exploding white dwarfs, exploding the type 1A supernova, exploding massive stars, the type 2 supernova. And so all these heavier elements come from supernovae. You wouldn't have those if it wasn't supernova. So as Joni Mitchell and Crosby, Stills, and Nash said, we are stardust. Most of us, other than parts that are iron less heavy, are from stars. So after the supernova occurs, depending on how massive the star is, it's not completely obliterated. So relatively lower mass, heavier stars collapse into neutron stars. And relatively higher mass stars collapse into black holes. So the end point of this whole process on the heavier end of the curve is the relatively less heavy stars end up as neutron stars, and the relatively heavy stars end up as black holes. So now we've looked at this process here. So red giant, type 2 supernova, remnant, cat's eye up here, and then here, this is the heavier, I can't read how heavy this is, but the heavier side become black holes, the less heavy side become neutron stars, which can be experienced as pulsars. So the three remnants of stellar lifetimes are white dwarfs, neutron stars, and black holes, as well as all the gas and elements that are emitted during these very explosive processes. Just a bit about differentiating supernova from each other, because now that you know how they occur, you can understand how they interpret some of these spectrographs. So, the white, sometimes referred to as thermonuclear type 1A supernovas, again, occur from stars that are mostly carbon. Their hydrogen has been exhausted, and so the spectrum lacks hydrogen. So these thermonuclear supernova type 1A, if you look for hydrogen in their spectrum, you don't see it. So when they do spectrographs of these supernova remnants, and they don't see hydrogen, then they classify them as thermonuclear type 1A. There are also other types subtypes of supernova that I'm not going to address today, but I'm going to differentiate 1A from 2. If you look at type 2, the core collapse type, again, they collapsed and had a remaining hydrogen layer. They didn't collapse because they ran out of hydrogen. They collapsed because they started trying to fuse iron into heavier elements, and they collapsed. And so when you look at their spectrum, type 2, you see a hydrogen. So that's how they originally differentiated these types of supernova. And again, I'm not going to address these because I still don't know about them. Again, if you look at these, there are the type 2 hydrogen spectrum, no hydrogen because there wasn't any when they collapsed. Type 1A, I wanted to show this because the type 1A supernova are always the same absolute luminosity. So they become very cool things because if you always know the absolute luminosity of something, and then you can measure its relative luminosity or magnitude from Earth, you can calculate distance. Because the relationship between absolute luminosity or magnitude and relative luminosity or magnitude is determined mainly by distance, in addition to whatever intervening gas or stellar dust might be there. So these become what are called standard candles. A standard candle is an astronomical object that has a known absolute magnitude. So thereby measuring, so if we measure apparent magnitude and can infer absolute magnitude by what type of object it is, we can figure out how far these are. And then we can figure out how far, so we have a ruler then that we can measure distance from. And we can use these type 1A supernova as rulers, or standard candles, which is the astronomical reason. So, in summary, the points to remember is that stars form from interstellar gas and dust. A star's characteristics are determined by its mass. A star spends most of its time in a position, the same position on the main sequence. It doesn't pursue a sequence of events until it leaves the main sequence. Its mass determines where it lives on the main sequence, how long it will live on it, and what its path will be when it ultimately dies. Low to average mass stars evolve through red giant phases and ultimately become white dwarfs, and perhaps planetary nebula, and perhaps type 1A supernova, if it's in a binary system or somehow manages to acquire more fuel when it's in the white dwarf phase. Massive stars evolve through red giant phases and ultimately die as type 2 supernova. Additional points are that supernova can be distinguished by the spectrum, and that almost all naturally occurring elements heavier than hydrogen and helium have been formed by stellar fusion through iron, and by supernova explosions for elements heavier than iron. And so just let me share some of the resources I got this. So this is the book I read, which is a really cool book if you're a beginning astronomer. It's got a bunch of little self-tests so you can teach yourself with it. Sky and Telescope magazine this May had Stellar Autopsies, which is a nice review of this topic. I read a lot of stuff in Wikipedia. I'm a big fan of YouTube after actually making this talk. I wasn't so much beforehand, but these guys have, this guy named Phil Plait has something called a Crash Course in Astronomy. Very good, very consistent with all the academic literature that I was able to find. He's very good. He's a PhD astronomer. This Michael Van Biesen guy has a series. He does everything, but he's got a series called The Nature of Stars, parts 1 through 37. That's really good. National Geographic has a really cool series called Stars 101. There's one called Professor Dave Explains. And then just on Friday, I was listening to my list of podcasts, and Shortwave, which is an NPR podcast, had one called Some Stars Explode as They Die. We look at their life cycle. So it's kind of a cool review for me looking at this. And that's, I think, all I have to say. Thanks for your attention. Question?
Could you rewind to your first page for your first page of resources?
Oh, first page of resources. Yes.
Yes.
Douglas.
I think I've been seeing more recently about another path that they've been getting more evidence for. It's the direct collapse now.
Huh.
And the stars are so massive, they just collapse to a black hole. They're supernova.
Wow. So they're so massive that they don't even release light as they
Those
collapse.
supernova, they collapse and the black hole forms. Everything's already inside.
Yeah.
There's no rebound, no explosion.
Yeah.
And they've been seeing it, and more evidence with more telescopes up in space and surveys. Stars that are they're gone.
Yeah.
They never see an explosion, they're gone.
Wow. Very cool. Other thoughts or questions? Or comments, Doug? Well, great. Thank you. I'll enjoy the rest of the day.